scaling, and today we're going to go back into things that are slightly more rigorous, maybe slightly more boring, but I hope basically the aim over the next 4 or 5 lectures, including this one, is to try and basically flesh out the story that we told yesterday, and try and make most aspects of it rigorous. So are there any questions about what we had yesterday? If there are any questions, you can take them now and then go on. Okay. Yeah.
Is there any particular reason to hold effective field theory to be really valid at the horizon?
Well, effective field theory, you expect, as I said, you expect it to be valid whenever curvatures are small. So because if you look at the quantum effective action, you expect it to have terms which are curvature squares suppressed by Planck scale squared. So you expect effective field theory to be valid when curvatures are small. And if for some reason effective field theory breaks down even when curvatures are small, that would be something very dramatic. It would be a breakdown of effective field theory in a region where you don't expect it to break down. So you would like to understand that much better, and it would be it would be an extremely dramatic phenomenon if that happened. So in general,
for example, if it's an ADS, you have another length scale which is the ADS rate. That could be set as one of the expansions. So R.
Yeah, but no. The ADS radius is not something that enters the expansion. The cost. You never do when you do effective field theory. The coupling constant for gravity is what controls what the parameter in the expansion is. The coupling constant for gravity is dependent on the Planck length. It's not dependent on the cosmological scale. So in our universe, for example, when we do an expansion, we don't do an expansion in terms of the cosmological scale. We do an expansion in terms of Planck scale. That's because gravity gets strongly coupled at the Planck scale, not the cosmological constant scale. So the ADS radius is the cosmological constant. That's not the correct parameter to effective field theory. You can see that from the leading coupling constant, which has Planck mass. It doesn't have ADS scale. Okay, very good. So we will continue today, and today what we are going to do is we are going to discuss quantum field theory in curved space. So just to tell you how we will do this, we want to discuss quantum field theory in curved space as a prelude to discussing Hawking radiation. So today we won't discuss Hawking radiation directly. In fact, we are going to not deal with black holes today, but I just want to give you the basics of quantum field theory in curved space, which some of you may have seen and others may not have. Can I get a sense of how many of you have seen at some point quantum field theory in curved space? Oh, so very few. Okay, but nevertheless, let me say it's not a subject in which you need to be scared of anything. It's a subject in which our development will entirely parallel the development of ordinary quantum field theory. So we'll do a development entirely analogously to that. And in fact, we're only going to be dealing with free fields. Okay? So the only thing that will be slightly different is that these free fields may couple to the background curvature, and so that's something that will be different. And the other thing that's going to be different, which is the one point, if I had to make one point, which I want all of you to take back, it is that the notion of whether there are particles in a space or not is an observer-dependent notion. Okay, so the question of whether you see an observer sees the vacuum in which there are no particles, or whether the observer sees a bath of particles, is something that depends on the observer. This is not something that you encounter usually in quantum field theory in flat space, because there's a preferred set of observers who are inertial observers. Okay, so there are inertial observers, and there are other Lorentz transformations you can make, which take boosts and rotations you can make, which take you to other inertial observers. But the moment you start considering accelerated observers, and if you're considering curved space-time, you have to consider accelerated observers, because in the end, if you're in some region where there's curvature, by the principle of equivalence, that's the same as having acceleration, and therefore it's important to consider accelerated observers. And the moment you start considering accelerated observers, and this is the one point I want all of you to take back, we will find that the notion of particle is observer dependent. Okay, so if I want you to take one slogan from all of this, it's that okay. So this is one thing I'd like all of you to understand. Once again, we are going to be slightly, there's some issue.
It's not working at all.
Oh, it's not working at all. Okay. Can you read this at all? Can you read this at the back? Maybe you guys should come up front if you can't read it. Huh? I don't know how to turn off these ones. Okay. Actually, I'm happy one of you comes up and does. Maybe these ones get turned off from there, so I'm happy whatever you do with the lights. If you can't see them, I'd encourage you to come up front. There's some spaces up front. So, okay, good. So this is the fundamental lesson that I want you to take. So we'll start with
all the lights.
Okay, so we're going to start by discussing just a free scalar field in curve space, and that's in fact all that we'll need for our discussion. Okay. So how does a free scalar field couple in curve space? So there is what the kind of scalar we're going to consider is what's called a minimally coupled scalar, where you take the action in flat space and you covariantize it. Now you make it generally covariant, but you make it generally covariant in the simplest possible way. And so therefore the action that we will consider so this is the simplest kind of action that we can consider. Of course, we can add a mass term. And this action in flat space reduces to the usual action in quantum field theory of a massive scalar that you're all familiar with. In curve space, there's some coupling. You can't read this at all.
There is a reflection from the.
From what?
There is a reflection from the.
Actually, what will help is if you come towards this side. I think the reflection.
I'm going to come to
So I can see it much better from here. So that side probably will be much better.
So if you guys can sit here, it will be great because one blackboard may make it difficult for the class.
There is plenty of second space if people can just shift there.
Yeah, so if you guys move out there, that will be great because one blackboard may make it a little difficult. I mean, I can try doing everything on this blackboard, but it's a little small, so it'll be great if you still can't see that, then we'll can you? So we'll continue now with these excellent repairs done. so now actually you guys I think you can all see right from the back. So already changed your seating arrangement. So let's leave it at that. So I think let me just go back to what I was saying. I want to discuss today. We want to discuss quantum fields in curve space, and the central message that I want to give you is that particles are observer dependent, and I also want to emphasize that this is what we're going to talk about is actually something rather simple. Don't get scared by anything that's happening. It's all just free fields and linear algebra, and linear algebra in function space, changing modes and so on. So it's very simple, but some of the consequences that we'll get are rather interesting. And not only are they interesting, they're also profound in the sense that, we will need them for Hawking radiation. And they're rather, important, and they're basically enough to derive, many of the quantum aspects of black holes. So it's something simple, but yet it's something profound. Try to follow and don't get intimidated by stuff. Once again, I'm not going to be following any textbook, but I've put up my lecture notes. There are several good textbooks on this, including the textbooks by Birrell and Davies and Wall and Sean Carroll also, right? Which I haven't used myself, but Sean Carroll, the last chapter has this. So there's a Sean Carroll has a book on called General Relativity and Black Holes. So it has some title like that, and you can look at that. But Birrell and Davies is the standard textbook. Wall is slightly more advanced and slightly more formal, and this is perhaps the most simplified version. Okay, so look at that. But as I'm saying, what we're going to talk about is simple, so you can also just follow along in class. So we want to consider a scalar field, and a scalar field. When we want to consider a scalar field in curved space, we have to generalize the action appropriately. So that is general coordinate invariant, and this is the minimal way to generalize the action. This is what is called a minimally coupled scalar. It's minimally coupled because it's not quite like a free field in flat space. It has some coupling to the background metric, okay, but it doesn't have any additional coupling. There are many other kinds of terms you could write down, which would reduce to the same thing in flat space. So this is not a unique generalization to curved space, but it's a minimal generalization to curved space. And the other point I want to make is that in all that we are going to do, we are going to neglect the dynamics of the background metric itself. We're going to take the background metric to be something fixed, and then consider these perturbative fields that are propagating about a fixed background metric G mu. Okay. In fact, if you want to consider gravitons as well, you can consider that, and consider that also as gravity waves propagating about a fixed background metric. So the general principle in all of quantum field theory in curved space-time is not to try to consider the full dynamics of the metric, but rather to take a fixed background metric and then consider perturbations about that background metric, as we are doing here. So there's a fixed background metric, which may in fact have been formed by some density of the same scalar field as we had the Oppenheimer-Schneider collapse, but then we are considering perturbations about this background. Okay, so this is the general problem, and this is called a minimally coupled scalar. And you can look up more about this, but we will now derive some simple consequences. So the first consequence has to do with what the Euler-Lagrange equations are. So the Euler-Lagrange equations are the usual Euler-Lagrange equations given in action, and they lead to the following equations. And this is sometimes called, this term is written as box. This is sometimes called box. These equations just follow in a very straightforward way by looking at this Lagrange. Okay. So if you look at this Lagrangian, you derive the Euler-Lagrange equations. You can get these equations. Is it clear to everyone how you get these equations? Not clear to some. All you have to do is, you have to look at the derivative of this with respect to the derivative of the field, and then differentiate that. Okay, so it's a usual way of deriving the Euler-Lagrange equation. This is just coming straight from that. Nothing complicated. We can discuss this more in the tutorials if there are questions about how you get this equation. Okay, so now the thing is that we have these classical solutions, and these classical solutions form a linear space. The reason they form a linear space is because this is a linear PDE. Okay? So the set of classical solutions forms a linear space. It's a linear space, as I said, because it's a linear PDE. However, when we want to quantize this, there are two kinds of approaches you can take to quantization. One of them is to try and use a path integral, but another one, which is somewhat more straightforward, has to do with using canonical quantization. Right? But when you do canonical quantization, you need a notion of momentum. So the canonical commutation relations that you impose are between the canonical degrees of freedom and their canonically conjugate momenta. Now the momentum is defined as the derivative of the action with respect to the time derivative of the degree of freedom. So you look at the Lagrangian and you look at the derivative of the Lagrangian with respect to time derivative of the degree of freedom you're considering, and that gives you the momentum. But implicit in this is some notion of what time is. Right? So therefore, before you define the canonical momenta and before you try and write down the canonical commutation relations, you need a notion of what time is. Now the key thing in curved space, which is different from flat space, is that there is no canonical so there is no canonical notion of time, and this is an important fact. Now you might say that there's no canonical notion of time in flat space as well, because you can do Lorentz transformations, and that's true. You can do Lorentz transformations, and the time for one Lorentz observer is different from the time for another Lorentz observer. But all of these different Lorentz observers agree on what the notion of the vacuum is, and they agree on whether particles exist or not in the world, and I'll show you in a second. And all of these different Lorentz transformations have the property that they take positive frequency solutions to positive frequency solutions. Whereas here, we are now allowing ourselves to make more general choices of time. And as we will see, this doesn't always respect the fact that positive frequency solutions go to positive frequency solutions. So this is an important fact, which leads to this. This is as a result of this that this fact follows. Okay. So in any case, let's make some choice of time, which we don't have to specify for now, but when we take a concrete example, we'll specify it. Let's choose some choice of time, t, the same as x0, right, the 0th coordinate. And there's some observer who decides that this is the choice of time that's appropriate. For this observer, you write down the canonical momentum. So you want to get it by looking at the derivative of the action, and this is given by okay. So you get the conjugate momentum by differentiating, and this is the form of this. Is it clear so far to everyone? Okay.
Can you elaborate once more what is meant by canonical notion of time?
There's no canonical notion of time. There's canonical just means that there's no universal notion of time. There's no natural choice of time, nor is there a natural family of choices of time as you have in flat space. In flat space, you have the times corresponding to different inertial observers. Here, you don't have that. Just to explain, well, I can explain more detail. You see, the thing is that imagine some space-time. So let's say you have some space-time which has something of this kind. One observer might decide to use a time that does this. Might decide to use slices that do this. Okay. So the time according to this observer is some particular thing that takes you from this slice to this slice. Okay. Another observer might decide to use a different notion of time. Might decide to use slices that are in this coordinate system that are flat. So all of these are foliations of the same space-time. So there's one four manifold, and you can foliate that in different ways. You can divide that into time and space in different ways. Here are two examples, and of course you can draw an infinite number of examples. And all of these are equally valid notions of time. You see, it's some foliation of the four manifold into a Cauchy hypersurface, and then some notion of time. But how this time behaves in the interior is clearly dependent on what kind of coordinate system you choose. Is this clear? Is this clear? So that we can't, if you're doing quantum field theory in curved space, there's no way of specifying how this, even if you say you're living in an asymptotically flat world, there's no way of specifying how this time coordinate has to behave inside, because all of these foliations are equally valid. So this is the usual thing that happens in general relativity. You can take a four manifold and you can divide it into space and time in different ways. Okay, so now let's say we impose these canonical commutation relations. So what are the canonical commutation relations? Canonical commutation relations are the usual ones, which say that I should have put time here. Right, so just for these few lines, I'm going to write time and space separately. Soon after that, I'm going to stop. I'm just going to write field as a function of x, which will include time. But just for the canonical commutation relations, I'm writing time separately as a coordinate. And that's because the way you impose canonical commutation relations is you impose them at equal time. Right? So the canonical commutation relations are So these are the canonical commutation relations. Are all of you with me so far? Yeah. So this is the standard. I'm not doing anything. I'm just doing the standard quantization. You have some field. You have some set of classical solutions. You quantize them in this way. Now the thing is that you can choose a basis for these, because remember I had written earlier that this is a linear. The set of classical solutions is a linear space. So you can choose some basis for this. So let's choose some basis, and I'll tell you what's the convenient choice of basis. Let's say we choose a basis, so that we write these. Now what we want to do in analogy to our notion of quantum field theory in flat space is we want to write down creation and annihilation operators. We want to introduce creation and annihilation operators, which is what in the end tie up to our notion of a Fock space and whether they're particles or not. So we want to introduce creation and annihilation operators. Okay. So we write the field as. Basically, in the end, when we do an example, this sum is going to turn into an integral, because of course, in fact, if you have a space which is non-compact, you have an infinite number of modes. But anyway, let's write this as a sum for now, because we don't. Yeah. Thanks. But this sum I runs over some complete basis of the set of solutions to the linear differential equation that we wrote down. Okay. Now if you compute, what phi of tx into phi of tx prime is, you can work this out, and you just take this expression, you plug in that expression for phi, and you'll get some expression for phi of tx into phi of tx prime, and the result is that the result is this is equal to I delta of x minus x prime if two conditions are satisfied. The first is that AI Aj dagger is equal to delta Ij. Okay. So this AI into this Aj dagger is delta Ij. This is the usual harmonic oscillator relation. And these mode functions satisfy the property that so provided these mode functions satisfy this property, and we have this set of commutation relations for these operators, and of course AI Aj equal to AI dagger Aj dagger equal to 0. Okay. Okay. So provided we have that AI Aj dagger is delta Ij, and AI Aj and AI dagger Aj dagger, the mid commutator is 1 and the self commutators are 0, and the canonical commutation relations, which are these ones, will be satisfied. Okay. Now, for those of you who are, so once again, as I said, there's nothing to get intimidated here. If you just put in, what are these mode functions in flat space? They're plane waves, right? So they're just e to the I kx plus I omega t, right? And e to the I kx minus I omega t. So now, if you just put in what these mode functions are, in flat space, you can check that. So what's this g0 mu in flat space is just g00. So it's just 1. This root minus g is just 1. So this term is basically just e to the I k into x minus x prime integrated over all of k, and that's why it gives you delta of x minus x prime. Okay. So this term is not something deep. It's just e to the I k into x minus x prime integrated over all of this. And the reason there's no t term is because there's an e to the I omega t and e to the minus I omega t. You're evaluating it as the same t, while you're integrating over all number of modes, and this I runs over all k. Okay? So this is very familiar to what you have in flat space. It's the same thing. There's just some other completeness relation. And in general, these may not be plane waves because you may be in a metric that's not a flat metric. So there's nothing very, very deep here. And now the vacuum. Okay, so the vacuum is defined by AI omega is equal to 0 for all I. Okay? So the vacuum is defined as a state that's annihilated by all the annihilation operators in this basis. But now the important thing is that when you talk about these annihilation operators clearly depend on what basis of solutions you chose. Somebody else may have chosen a different basis of solution, and then that somebody else who chose a different basis of solutions and a different coordinate system, which was tailored to his or her own coordinate system, would clearly, use a different basis of creation and annihilation operators, which would be equally good, but which would not satisfy that AI on the vacuum is 0. Okay? So let me just try and make that a little more precise. There may be another person who chooses different relations, which are BI, GI, there could be somebody else who just chooses to expand it in terms of a different set of solutions. May also be using a different set of coordinates. Doesn't even have to be using the same t and x coordinate. Doesn't have to be using the same t. Could just be using a different set of coordinates. So now the point is that because we know that because both of these are complete bases of solutions, there has to be a linear transformation between these bases, right? And therefore, it must be the case that there should be some coefficients which have the property that AI is equal to sum of alpha ji ej plus beta ji star j dagger. And of course, AI dagger is a complex conjugate of this, right? So it's alpha ji star bj dagger plus beta ji j. Okay. These coefficients, alpha and beta, are called the Bogoliubov coefficients between these bases, f and g. So these coefficients between AI and BI, between F and G, or whatever you like. There's the basis is labeled by either A and B or by F and G. Okay?
Sir, this AI and BG are linearly related.
These are what?
You said like these are linearly related.
A and B are linearly related. That's right.
Why is that?
Good. So the reason is that this complete basis of solutions, F and G, are both the basis of solutions, right? So if you make, this is an expansion of a field which is a solution to the wave equation box 5 equals 0 in a certain basis of functions. You can use the basis of functions fi, or you can use the basis of functions gi. But it's just it's an expansion of a function in another basis. If you change the basis, the coefficients are linearly related. If you change the basis from gi to fi, you get some linear relation between the coefficients. That's why they're linearly related. I mean, this is just linear algebra. There's just an expansion in a complete basis of solutions of some linear differential equation. You can use a different basis, and the coefficients in the different bases are related by linear equations.
We usually not get in BI that BI of omega is 0.
We will usually not get BI of omega 0. I'm coming to that in a second. That's right. You will usually not get that. But before that, let me just give you some tutorial questions just to familiarize you with this. The first question is.
So this AI and BI could be say, so GI and FI could be say plane wave solutions to study the waves.
For example.
Which they would create particles in the momentum state or angular states.
For example, they could be that, or they could be more general. But it's true that they could be that, for example. That's it. That's an example. Yeah. Okay. So tutorial. So 2 questions. FI and GI. Okay. So if if AI and BI have this relationship, what is the relationship that FI and GI have to have? Second, this is an easy question. Second one is also easy, but if BI BJ dagger is equal to 1, so if BI is also satisfied, the same normalized that BI BJ dagger is 1. Find the constraint on alpha beta. So these are both questions of linear algebra. You have a relation between A's and B's. You plug this in, you get a relation between the F's and the G's. It's a question of whether you make an active or a passive transformation of basis. Given these relationships between the A's and the B's, you can check that if BI BJ dagger is 1, then that gives you some relationship between these alphas and betas. If alphas and betas are totally arbitrary, you won't find that it's consistent with having both AI dagger 1 and BJ dagger 1. So the question is, what is the constraint? So the question is clear? Okay, so these are simple questions, but I think it's important that you try and work them out so you can get a feel for these Bogoliubov coefficients too.
In flat space-time, since FI is Lorentz invariant, so we'll get AI is equal to beta.
In flat space, it's no, that's not necessarily true. You may have, even in flat space time, you can have, for example, all sorts of changes of basis. For example, this one, where the AI is one of them is spherical base and the other is plane base. Even if you make, other kinds of transformations, you will have these various changes of basis. In fact, in flat space time, all of these things still hold. These things still hold even for Lorentz transformations. There are some coefficients that you would get because these operators transform. So these things are good for Lorentz transformations as well. What won't happen, I'll say in a second what will happen here that will not happen usually in flat space-time. It's actually not even a question of whether space-time is flat or not. It's a question of what kind of solutions you restrict to.
So, sir, number operator will be the same.
Oh, 1 second. Number operator will not remain the same.
In the flat space-time?
Well, we'll discuss flat space-time in some detail. So, it depends on how you slice flat space-time. You can slice flat space-time also in funny ways so as to not make the number operator the same. What you're talking about maybe is what happens if you make Lorentz transformations. So if you consider a set of slicings of flat space-time which are related by Lorentz transformations, that's a slightly different set. For inertial observers are those ones who are related by Lorentz transformations.
The fact that you have a mode expansion
Yes.
of 5,
Yes.
so I presume that your minimal coupling does not change the eigenspectrum of the Hamiltonian, which is typical still equispaced harmonic oscillator spectrum. But otherwise, how would you have a
Well, the eigenspectrum of the Hamiltonian in general is something which is continuous. So it's always.
It remains the equispaced.
There's no.
Once you quantize it, it still remains the equispaced. So how will you have your particle interpretation?
Right, so that is certainly true. If you take a given frequency, if you take one of these modes, it has some commutator with the Hamiltonian, and it's certainly true that you construct a Fock space the way you usually do. So maybe I should have said this. Starting with the vacuum, both A's and B's can construct their Fock space. So this is the A vacuum. Okay, A can construct a Fock space which is given by, so this leads to a Fock space. AI1 dagger, AI2 dagger, so on. AIN dagger on omega A. Right? So this gives you the Fock space. Similarly, B can construct his or her own vacuum which corresponds to B of omega B is 0, and then construct a Fock space on top of that. And it's true that if you add with 2 B's, that gives you twice the energy of acting with 1 B.
So the eigenvector name is equi-space, and that's why you are able to have a more expansion.
That's it. It's still a Fock space. It's still a free field, right? And this leads to BI1 dagger, BI in dagger. It's the B Fock space. Yeah.
Here we are considering general space-time, right?
Yes.
General part space-time. So can we always locally find the transformation so that GIs are plane waves?
I didn't say G as a plane waves. I never said G as a plane
Can
waves.
I always locally?
What does it mean, locally find a transformation?
Because in GR we know that locally you can always.
You can always locally go to a coordinate system where these solutions have a certain form. That's certainly true. If you want to just make them look as e to the, locally plane waves is actually a misnomer, because that doesn't actually mean. What does it mean for something to be a locally a plane wave? A plane wave is a property of a solution which extends all over space-time. There's no such thing as a local plane wave. Plane wave is something which it's a plane wave. It goes all the way out to something. At any given point, you can always write something as e to the I. What does it even mean to write it as e to the I kx? You can write anything as e to the I kx, right, with some coefficient. So plane wave especially has to do with properties of things. It's a non-local concept. It's not a local concept. Okay, good. Now, in particular, the key point is that the notion of a vacuum is not the same, because the A vacuum which satisfies AI and omega A0 is not the same as the B vacuum which satisfies BI and omega B is 0. So in particular, it may be that one of these people thinks that they are in the vacuum, whereas the other person thinks that they are not in the vacuum. Okay? In fact, it's very simple to work out what the relationship between these different vacui is. And the relationship is worked out as follows. You see, if I say that AI on omega A is equal to 0, that is the same as saying that sum on alpha ji bj plus beta ji star into bj dagger on omega is 0. Omega A is 0. This is just a definition. It's the same thing, because AI is given in this form. But, consider, so now the question is, can you write the A vacuum in terms of the B Fock space? See, in the end, the full span of states that you get is the same, although which state somebody calls a vacuum and which state somebody calls an excited state is different, but the full Hilbert space that you get is the same. So the question is whether you can write the A vacuum in terms of the span of B states, and the answer is yes. And here's a simple way to guess this. So let's try an answer, which is omega A is equal to e to the half bj dagger cjk k dagger on omega B. Okay. Why is this a good answer to try? You see, if you've seen the simple harmonic creation annihilation algebra, you know that these D's can also be realized as D by dBj dagger. You can realize the simple harmonic algebra of B's and B daggers also as the algebra between X and D by dx. Right? So if you have a state of this kind and you act on it with a B, it pulls down a Bj dagger. So if you have a state which satisfies B plus B dagger on omega is 0, that's the state which is of this kind. It's a state which has an exponent which is quadratic in the B daggers. Have you seen this before? Okay. Let me give you an example. Forget about the indices for a second. Okay. Have you seen coherent states before? So coherent states have the property, here it is. Okay. So taking an aside, detour. So there's no i's and j's, okay, just one a, just one simple harmonic oscillator. Coherent states have this property. Okay? If you act on it with an A, you can check that they satisfy the property that A on Z is Z on Z. So they're like eigenstates of the equation. The quick way to see this, okay, is to realize the algebra of A's and A daggers, okay, as the algebra between x and d by dx. You see, d by dx and x is also 1. So this, the fact that z is this and this is this, a quick way to see that is to think that when you have a state of this kind, the action of A is just like pulling down a d by dA dagger. And you can check that by using the commutation relations between the A's and the A daggers. You can check that easily. But in particular, if I now consider a different state, what should I call it? Let me call it y, which has the property that you write it as e to the y A dagger squared on the vacuum. Okay, so this is a different state, not a coherent state. Okay. Then this state satisfies the following relation, which is that A on y is given by A dagger into y into omega.
So one question, this H and G bases are related by Bogoliubov coefficient. Similarly, this omega A and omega B can be related with Bogoliubov coefficient.
I'm giving you a second. I'm telling you what omega A and omega B are. This is the relation between omega and omega B. I'm just motivating it first. There is a relation between omega and omega B, but I'm motivating it first.
So what you are doing is using the formula A comma f of B commutator is f prime B into A commutator B.
A comma f of B commutator is sorry, that formula. Maybe I'm using that formula. It's something where we can check if I'm using that formula. But it's something that's much simpler. It's something you should all know. The algebra of creation and annihilation operators can also be realized as the algebra on function spaces as of d by dx and of x. Okay? So if you think of the set of functions f of x as the set of spaces f of A dagger acting in the vacuum, then the action of A is just like the action of d by dx. So this is an example. Coherent states are one example. You take a state of this kind, you differentiate it, you get this. You take a state of this kind, okay? You act on it with A and you can check you will get A dagger y on omega. Okay? You should check this. We can so please check it by the tutorials. You can check it easily. And as a result of this, you have something more complicated. Here you have some. You don't have B is equal to B dagger, but you have some linear combination of B's acting as giving you some linear combination of B dagger. So you should make a guess of the same kind, something that's quadratic, but you have to make sure it might mix different modes. That's why you have a matrix here, whereas here you have just a number. Okay? In the case of one harmonic oscillator, you just have a number, whereas in this case you have a matrix. Okay. Are all of you following so far, or are you following the idea at least? Okay. So from here. The question is, what is this CJK? Of course, this CJK by the way has to be a symmetric matrix because this is BJ dagger into BK dagger, so you don't care about the antisymmetric part of CJK. But you have to check, what CJK is, and you can easily check that sum of alpha Ji. If this is the ansatz for omega in terms of omega B, then sum of alpha Ji B J. J's and I's look similar, but look for the small curve at the end, which indicates that it's J and an I. It's a bit of a research problem, but okay. That small curve is that it's a J. So alpha Ji into beta J is given as alpha Ji. Under this ansatz, okay, and you can check that this basically implies, that sum of Cmj into alpha Ji is equal to beta star mi, And this is a statement that C is roughly A inverse B. Okay, in terms of matrices, if you now invert this alpha, you find that C, B A inverse. In the index notation I'm using, it's beta A inverse, beta alpha. Okay, so this is, you can just check, if you have the correct solution to something like this is to use C's beta alpha inverse, and if you insert that up here, you'll get a state. So this is a relation, by the way, between omega A and omega B, and it is related by the Bogoliubov coefficients.
Then you have beta star alpha inverse.
Oh, yeah, beta star alpha. That's it. That's it. Thank you. Yeah. So you can check that that's the relation between the C's and the alphas and the betas. And but the essential point is that if you look at the A vacuum in terms of the B vacuum, so the A vacuum is not only an excited state; it's a specific excited state. It's a state that has these two particle pairs that are produced on top of the A vacuum. Okay? So the A vacuum is not one particle on top of the B vacuum. It's not even two particles on top of the B vacuum. Rather, it's this generalization of a coherent state which has these two particle pairs, but an exponential of these two particle pairs produced on top of the B vacuum. So there is a specific relation which is determined by the Bogoliubov coefficients for the number of particles seen by the A observer and for the B observer. So there is a specific relation between the vacua, and this is making precise the statement we made at the beginning of this lecture, which is that the number of particles is an observer-dependent concept. How is it an observer-dependent concept? In this sense, that if observer A obtains a vacuum and there is a set of Bogoliubov coefficients which you have to give me at first, then I can tell you what observer B sees. Observer B thinks that the A vacuum is a set of two particle pairs excited on top of the vacuum for B. So is this result clear?
So another thing I have seen from here is that if I operate Bi over omega A, it's simply Bi is a linear combination of A and A data. So that will give me some non-vacuum mixture.
Bi, that's it. So of course you can write omega A in terms of omega B. You can reverse this. You can write omega B as an excitation of the A vacuum. You can do that as well. Yeah. So of course it's true that if you want to act with Bi of this. Yeah. So there's an equivalent relation that's there's a symmetric relation between the A and the B vacuum and the B and the A vacuum. So it's true of course that the Bi acting on omega A is not zero. Clearly Bi acting on omega is not zero, right? Bi acting on this is it has many excitations. It's not the vacuum. Okay. Are there any questions about this result? It's what we're doing is really it's simple linear algebra. So if you're not following this, just go back and look at it, and you will see that it's simple linear algebra. Or look at one of the standard textbooks; they will give you this answer. Yeah.
So you could have a Bogoliubov transformation even in the flat space.
Yes.
Right? So, but I would not expect to have this weird result in the flat space.
Correct.
So what is
The betas are zero in flat space.
sorry?
The betas are zero. The annihilation operators are the same as the other annihilation operators. They don't have any equal to the creation operator. The beta coefficients. If you make not in beta, when I say in flat space, I mean between different Lorentz observers. The betas. Okay. So what is the invariant physical quantity? Okay. So one last point about generalities, and then we'll go on to a concrete example. What is the invariant? What is the invariant statement? The notion of the vacuum is not invariant. What is it that is invariant? And this is a second important point. The thing that is invariant are correlation functions of the field in a given state. And so what you should really look at are correlation functions of the field in a given state. So if you look at this, whereby this correlation function in a state, you could take this to be any state. You could take this to be the omega A state or an excitation about the omega A state. But if you look at these correlation functions, they also give you information about the state. And these correlation functions are invariant, of course. They don't depend on which observer calculates them. So the physical statement is, what is the physics of the statement? The physics of the statement is you might have two observers who are using different bases to describe their world. But if they try to measure the correlators between the field at one point and the correlator between the field at the other point, there they will get the same result as long as they're measuring the field at as long as they've agreed on which points to measure it at. So what is it that observers agree on? They agree on correlation functions. They don't agree on whether things have particles or not, but they do agree on correlation functions. Okay, so this is something that's important. Let me mention a subtlety which may not be relevant. So if those of you who don't want to listen to the subtlety, if you can switch off for 1 minute. The subtlety is as follows. Sometimes people try and define a renormalized operator which is phi of x squared. Okay? So they try to define the product. This is when, here in this correlation function, x1 is not equal to x2. So these points are separated. It's not the same point. Sometimes people try and define the product of fields at one point. This product of fields involves doing a renormalization. There's some normal ordering that goes in here in free fields, and more generally it involves a renormalization. This may depend on frame because renormalization may depend on frame. Because the normal ordering may depend on the frame. Okay. Now, why is this relevant? Why do I mention this? You see, at times it may be that you want to compute the stress tensor. You want to compute the stress tensor seen by an observer. You want to ask, does an observer see finite energy density or does an observer not? In defining the stress tensor, you always have to define the renormalized product of fields at a point. And in that renormalized product of fields, the frame enters. And therefore, even though I'm saying, and it's true that correlation functions are the same as measured by observers, the notion of the stress tensor, which actually tacitly always involves some renormalization, may not be the same. So if you read this literature, you will find often people computing stress tensors and finding that they're different for different observers, and then you might wonder how to reconcile that with this, and the reconciliation is from this time. That the renormalization may be frame dependent. In fact, this is, if you want to see, this is actually discussed in this book by Di Francesco. There's a big yellow book by Di Francesco et al. I think in chapter 6, something like that.
So but then why does the anomaly answer cannot be the same?
What anomaly? There's no anomaly there.
No, I mean if I'm calculating for T mu, let's say I calculate T mu or bracket T mu. The result, before there used to be literature saying we are getting different answers, and then that was resolved. So
this is there's something more fundamental happening here. It's a question of what is happening in a given state. It's not a question of so it's not a question of whether so if you write down something that's proportional to some curvature term, for example, that curvature term is of course something that happens to be the same. Is proportional to a curvature of the background metric. That's something that people might see, but this is something that's more fundamental. It's much simpler than that. There's no anomaly here. It's just a statement that one observer might observe finite energy density and the other might not, and that is still consistent with the fact that correlation functions at separated points are the same. It's consistent because as you take the 2 points to each other, these two observers are using different renormalization prescriptions.
Right, I was trying to. There's a
Okay, so now I said all I want to say about generalities. Now I actually want to go back to flat space and work out an example that demonstrates these features. So I will try and do this in about half an hour, so we might go about 10 minutes over time, which is the 10 minutes we lost first. So, okay, so just to finish this, so now I want to go back to flat space. So I've said everything I want to say about generalities, and let's go back to flat space and show how these notions apply even in flat space. In fact, we are going to consider a very simple example, which is flat space in 2 dimensions. So just flat space in 2 dimensions. So let's just take flat space. Okay, and I'm now going to, you can quantize this flat space in 2 dimensions, and you can define a U. what the metric as usual is okay. Now you can consider a different coordinate system, which is a different slicing of flat space itself. Okay. This different slicing is what's called Rindler space, called Rindler coordinates, and they involve introducing some new coordinates in the following way. Writing U, so I'm now going to draw two light rays. This is the light cone that passes through the origin. This is the line U is equal to 0. U is equal to 0. Okay. This is 1, 2, region 3, and 4. This might actually remind you of a diagram of the Schwarzschild black hole as well. But for now, it's just flat space. Okay, it's just flat space, and I've introduced these coordinates U, V, and I've divided the region into 4 quadrants, depending on whether U is positive or negative, and whether V is positive or negative. Okay, so is this diagram clear to everyone? Okay. Now I'm going to introduce some new coordinates in region 1, which are defined as follows. U is equal to minus e to the minus AUR. V is e to the VR, AVR. Okay. Why do I put a minus sign? Because U is negative in this region. E is smaller than x. And then there's a minus sign here. And the new coordinates UR and VR are defined through these relations. Okay. So UR is like log of U and VR is log of V. And these coordinates are defined only in patch 1. Okay. Okay. So these are some new coordinates. What does the metric look like in these coordinates? If you look at the lecture notes, I introduced some additional factors of 1 by A. If you look at the notes I'll put up, I'm not going to use them in class. Actually, they're not important for anything. Some convention I copied from Birrell and Davies, but it's not important. So in particular, if you look at du dv, which is the metric that we had, see, that is just given by e to the twice to the a vr minus ur dur. And for these Rindler observers, we can introduce some additional coordinates, which are that you can write ur is equal to tr minus xr, and vr is equal to tr plus xr. Okay. So this, let me just say a little bit about the physical interpretation of these coordinates. What is it that we're doing? Of course, we're taking flat space-time and we are slicing it up in different ways. Even in flat space-time in 2 dimensions, I'm free to introduce some new coordinate patches that do this. This coordinate patch, by the way, is relevant only for region A. And then I can write down the new metric in this. So I can take flat space and I can write it in a funny coordinate system. And I can make life difficult for myself. The question is, why is it that I would want to make life difficult for myself and use this coordinate system? So the fact is, the central point is that these coordinates actually have some interesting physical meaning, which is that if you look at observers who are sitting at a constant value of xr in these coordinates, these observers are uniformly accelerated observers. If you look at the trajectory of an observer who is sitting at a fixed value of xr, then this observer is a uniformly accelerated observer. You see, what are fixed values of xr? Fixed values of xr correspond to hyperbolas here. Right? Fixed values of xr correspond to something like this. This is xr as fixed. Right? So xr is fixed corresponds to something that does this. And tr is fixed corresponds to something else, corresponds to these slices. Okay, so this is tr fixed and this is xr fixed. Okay. So, who is the observer who takes a trajectory of this kind? The observers who take trajectories of this kind are observers who are uniformly accelerating with an acceleration e. So, this is also a tutorial question. Today we have some number of tutorial questions. They're all simple actually. They all should take not more than 5-10 minutes. Okay, so you can show this. It's simple, and you can already see from the fact that you have this hyperbola these are trajectories. How many of you are familiar with this fact? Have you seen these hyperbolas being trajectories of uniformly accelerated observers? Only few. Okay. So it's not hard to check. Just write down the equation of a world line, which is uniform acceleration, and you will see that you'll get a solution, which is this hyperbola, which is this. Okay. So there is a physical reason to consider these coordinates. The physical reason to consider these coordinates is that these coordinates correspond to the coordinates that would be used by a family of uniformly accelerating observers. So there's a natural physical reason to consider these coordinates. And the physical thing we are going to find, which the formalism of QFT in curve space is going to tell us that a family of uniformly accelerating observers sees a thermal bath of particles, and this is called the Unruh effect. So the phenomena we are about to discuss is called the Unruh effect, which says that accelerating observer sees a thermal bath of particles. Okay. So this is the phenomena we are about to derive using our formalism that we developed in the first half of this lecture. And as I'm going to say tomorrow, this phenomena, the Unruh effect, is very closely tied to Hawking radiation. So the reason we are considering this phenomena is not only to warm up by considering QFT in curve space, but also to get something which is an essential ingredient into the derivation of Hawking radiation. In fact, an analysis of the Unruh effect, the Unruh effect was studied because of the discovery of Hawking radiation, and later it turned out to be the simplest way to derive Hawking radiation. So we'll do Hawking's derivation, but also this is the simplest way, and this captures a lot of the essential physics in Hawking radiation. So even though right now what we're doing is something very simple, we're just taking flat space and considering accelerated observers in flat space, in the end this is going to relate to Hawking radiation.
So basically, sir, this acceleration will be related to the surface gravity?
Right now there's no surface gravity. Let's talk about surface gravity tomorrow. Yes, it will be, but let's talk about surface gravity tomorrow. Right now it's just flat space. Yes, it will be related to surface gravity. Okay, so now let's write down what the metric is in these coordinates. You see the metric, this is just e to the twice axr, right? From this relation. Okay. So now let's notice that if you want to write down a wave equation, which remember was so now for simplicity I'm going to set m square equal to 0. So our wave equation becomes very simple. It's just okay. And what are the coordinates that we have here? Well, x star e to the minus twice axr. And this is the same as g tr. Okay. But root minus g is e to the twice axr. Okay. So just using that metric, we find that the inverse components of the inverse metric are this, and this is the determinant of the metric. Okay, is this clear? I'm just taking that metric and doing this. Very good. So now what's the wave equation? You see the wave, because of this, the root minus g cancels off with the g mu nu upper indices, right? So the wave equation reduces back to the wave equation in flat space. Even though the metric is not flat, the metric has this e to the twice axr term. The wave equation simplifies. The wave equation doesn't have any of these terms. So the wave equation looks very simple. The wave equation just becomes right? And therefore you can write down a solution for phi in terms of these xr and tr coordinates, which looks very much like the solution you had in flat space, in the Minkowski coordinates. And that solution, here, let me just explain some features of this solution. What are the solutions to this wave equation? You see the solutions to this wave, what are the solutions to this wave equation? They're plane waves, and they're plane waves which can have in two dimensions two kinds of properties. See, they can have the momentum equal to the frequency, or they can have momentum equal to minus the frequency. Right? The momentum in XR can be plus the frequency or can be minus the frequency. Depending on that, you would write down a solution that looks like e to the I omega TR plus XR or e to the I omega TR minus XR. These are the two solutions I have written here. Okay? So that their solutions XR plus TR and XR minus TR, and they I've integrated over positive frequencies only. And here these are what are called so the solutions where as TR increases, XR increases are the right moving solutions. These are solutions which have TR minus XR, so these are called the right movers, and these are called the left movers. Okay, where the lines of constant phase as TR increases move to the left. Okay, so these are called right movers and these are called left movers. These are called left movers. Okay. Secondly, why is this the annihilation operator, not the creation operator? This is an important thing. Why is this the annihilation operator, not the creation operator? Because for the Rindler observer, okay, this is the term that goes with minus I omega TR. You see, UR is TR minus XR. So the annihilation operator is the thing that multiplies e to the minus I omega T. That's why it's A omega into e to the minus I omega UR plus B omega, which is another set of annihilation operators, into e to the minus I omega VR plus Hermitian conjugates. The Hermitian conjugates are A omega dagger and B omega dagger. Okay, so this expansion is there. Okay. So this is the expansion for the field, but it's an expansion that's valid only for the field in region 1. Okay? Because these UR and VR coordinates were valid only in region 1. Now we want an expansion for the field in region 3. Right? So now, let's consider what happens in region 3. In region 3, you can introduce another set of Rindler coordinates, which are related to the usual Minkowski coordinates as follows. You see, I'll just draw a diagram also. So let me draw my diagram once again. Capital X, Minkowski, capital T, Minkowski, U equal to 0, V equal to 0. Okay, this is the region U smaller than 0. This is the region, there's the region, in this region U is positive. Okay. So now notice that I have introduced a second set of coordinates. This is for region 3. Now how do these coordinates behave? This is a set of coordinates. I've done another transformation. This is region 3. So this is 1, 2, 3, 4. In these coordinates, as U goes to 0, you see that U goes to 0 as UR goes to infinity. If you look back to the transformations we had for region 1, U goes to 0 implies UR goes to infinity. And that is consistent with ER going to infinity, okay, but XR going to minus infinity. Okay, so that's this region on top. Well, V is finite, so TR plus XR is something finite, but of course TR minus XR is infinity. On this region, you have TR going to minus infinity, but XR is again going to minus infinity, and therefore TR minus XR is something finite, because U is finite on this line, V is equal to 0, but V is 0. Okay? And that's because TR plus XR goes to minus infinity. There's no minus sign in the exponent. Okay? If you use these coordinates now in region 3, you will find that these lines have the same form. Okay? So this is still TR goes to infinity. infinity, XR goes to minus infinity, and this is still TR goes to minus infinity, XR goes to infinity. What does this tell you about the direction of TR in these coordinates 1 and 3? Exactly, so it's inverted. You see, in this coordinate system, in this coordinate, TR is running upwards. Okay? Whereas in this quadrant, TR is running downwards. Okay? So the correct time coordinate to use in this coordinate region 3 is actually minus TR, not plus TR. Okay? So even though I've introduced these coordinates for convenience, if you want time to run up everywhere, then the correct time coordinate here is minus TR, and the correct time coordinate here is TR. Okay? So this time is not the same as the Minkowski time, right? This time, remember I said, lines of constant TR are this, or something like this, right? So in this situation, time running upwards, pushes this line up and pushes this line up. Okay? That's increasing TR on this side and increasing minus TR on this side. Okay? So is this clear? How TR is behaving? Okay, are there any questions at this point about the geometry of this? If you have questions, stop me and ask. I'm happy to explain the geometry of this.
Does it mean that the UR will transform to VR and VR will transform to UR?
Which UR? So there are two different URs and VRs. There's one UR here which is defined as UR with a minus sign. In this region you have UR is minus, e to the minus AUR, and U, capital U is, and V is e to the AVR, right? In this region you have this relation. This is for this region. This relation is for the capital U and V, whereas in this region you have a different relation. So the UR, VR coordinate patches are defined differently in this coordinate and differently in this coordinate. The advantage of the definition, the sign conventions we're using right now, is that this line is continuously TR equals infinity and XR equals minus infinity. Okay? That's, it's a convention. I could always flip the minus and plus sign. But the advantage of the convention I'm using right now is that this line is constantly TR equals infinity and XR equals minus infinity. And a line of constant TR is a line that runs through this bifurcation surface. It's a convention. This is the advantage of the convention. The disadvantage of the convention is that TR runs up on the left and down on the right. You could always choose a different coordinate system where you flip some of the signs. Then you would lose these nice properties that, constant TR is a line that goes to the origin. And you would lose the property that this was, this line was continuous, was TR equals infinity and XR equals minus infinity on both sides. Okay? You could choose a different coordinate system and you could fix this, but we have chosen this convention and it has this disadvantage. So we have to be careful about this disadvantage. Okay? Okay, so now, you quantize the field in the same way and we'll write down expansion for the field in region 3. It's the same procedure that we did. The expansion for the field in region 3 here is integral d omega by root omega into some different creation annihilation operators into e omega tilde to the I omega ur plus e omega tilde into e to the I omega vr plus summation conjugate. Do you see a difference between this expansion and this expansion? Apart from the fact that the operators are different. That's right. This is plus. This is plus here. Now why is it plus? It's plus because of what we just said. See here you want the annihilation operator to have positive frequency with respect to the correct physical time, which is minus TR. Okay? So that's why you want this to go like e to the I omega into UR plus UR, because here you want it to go as e to the minus I omega into UR. Okay, that's the reason for the difference between these two expansions. Okay, good. Now, so you can write down now an expansion for the field which has the following property.
Sir, one question.
Yeah.
This E omega and B omega both are annihilation operators.
Both are E omega and B omega, that's right.
So
And A tilde omega and B tilde omega, all four are annihilation operators.
So this E omega and B omega, how they are related?
They're not related. They're independent annihilation objects. Right now, all these four are totally independent annihilation objects.
I'm sorry, just to remind you, your file is real scalar field, right?
Yes.
So you have A, B, and then A tilde, B tilde.
That's right. Right now there are four annihilation objects. Okay?
A omega annihilates the right moving.
A omega annihilates the right movers on the right side. A tilde omega annihilates the right movers on the left side. Okay, good. A tilde omega are also right movers, right? Okay, so now, so we have an expansion for the field which works everywhere in the following sense. We can define a mode function which has the following property, that UL this is a mode function, UL of U given by e to the I omega UR in region 3 equal to 0 in region 1. UR of UR equal to 0 in 1, 3 to 1 to the minus I omega UR in 1. Okay. VL of VR I omega VR in 3 0 1 and VR 0 3. So I've written a lot of things, but really I haven't. It's just these mode functions. I've just written these mode functions as things which satisfy the correct property in the region 3, and they're 0 in region 1. So in terms of all of these mode functions, which have this property that they're 0 and half on this side, and they're something else on this side, we can write an expansion of the full field as follows. So you can write in region 1 and in region 3 as integral d omega by root omega into a omega tilde ul of ur plus b omega tilde into vl of vr plus a omega into ur of ur plus b omega into vr of vr plus summation conjugate. This is now an expansion that's valid both in region 1 and in region 3. I've just combined this expansion and this expansion. Okay, so this expansion is now valid both in region 1 and in region 3. Okay, so this is an expansion of the field that now works for the whole slice at the Minkowski time t is equal to 0. But there is another expansion that you can write down, which is the usual Minkowski field expansion. You see, the Minkowski field in Minkowski coordinates also has a good field expansion. So we can quantize the field in the usual Minkowski coordinate, where it satisfies d by dt squared minus d by dx squared and phi is equal to 0, where t and x are Minkowski coordinates. Right? And therefore there is another expansion of the field which is written as plus d omega summation conjugate. Okay, So there's another expansion that we can write down where there's a profusion of creation and annihilation operators. But so there are 4 already that we have here: A, B, A tilde, B tilde, and now I've also introduced C and D. Okay, but these are all, both of these, this one and this one. So I'll erase the wave functions so as just to leave these wave equations so as just to leave these expansions on the board. These 2 expansions are both equally valid expansions for the field. Okay? These are both expansions for the field that work now, both in region 1 and in region 3. And therefore, there must be a Bogoliubov transformation between these 2. And using that, we can relate what the Rindler vacuum is to the Minkowski vacuum. Okay, I notice actually I'm out of time, so we can actually stop here and go on tomorrow. Because this will take about 15 minutes more, so maybe a better thing to do it tomorrow. Are there any questions about this part? So let me just set up the problem. I'll solve the problem tomorrow. The thing is that we said some general things about quantum fields in curved space, right? From those general things, we had these relations about what happens if you have Bogoliubov coefficients. And now, as an example of our general formalism of quantum fields in curved space, we are taking the example of taking flat space and quantizing it in Rindler coordinates. Rindler coordinates are coordinates that correspond to accelerating observers. So we are trying to see, we are trying to derive the Unruh effect, which is the statement that an accelerating observer sees a bath of particles. So far, all we've done is we've solved the wave equation in these 2 coordinates, and we've written, the relation in coordinate 1, in coordinate 3, in quadrant 1 and quadrant 3, and we've written down also the expansion of the field in these Minkowski coordinates. Okay? So now the question is that since these are both solutions of the same wave equation, there must be a Bogoliubov transformation that takes you from one to the other. So there must be some relation between these C omegas and D omegas and these A tilde, B tildes. Okay? So that relation we will find tomorrow and also derive what the Minkowski vacuum is in terms of Rindler space. So are there any questions about what we have done and what the problem is so far, or about the geometry of Rindler space, or what is happening?
So it might be a little better if you distinguish between R for right and R for Rindler, I think probably.
Oh, so this all of these are R for Rindler. Everything inside the coordinate is R for Rindler. Everything outside the L and the R has to do with left and right. Okay, I don't know how to distinguish it. I mean it's
That was a mode function.
That's right.
But now,
I mean, this mode function. It's what I've written there. I mean, so let me make this. Let me use my my small r or whatever.
No, make that thing inside smaller.
Because the thing inside,
because okay.
Yeah, the coordinates when you initially introduce small r.
Whatever, let's initially introduce them with small r. I thought I initially introduced them with capital R.
yes, sir, that was smaller matter, but this line DUDP was with capital R. So I thought that it was.
Okay. So don't get confused by this. This is something very simple. If you think about it, you'll see. There's no reason to get confused between R for Rindler and R for right. Okay, so there's one of them is modes which are non-zero on the right, one of them are modes which are non-zero on the left half, and Rindler coordinates are just Rindler coordinates. They're different from Minkowski coordinates. Everything on the top line has to do with only Rindler coordinates. This is the expansion in Minkowski space. The way you differentiate, by the way, is that everything in Minkowski space is capital T and capital M. Okay?
So the reason why you took the I omega UR is because you want minus TR as the physical coordinate.
Correct. Minus TR is the physical time. It's the direction of physical time.
Sir, this left part and right part of the signal, are they disconnected or they can be connected?
They're connected to the bifurcation point. They meet at one point, which is the point in the middle, the origin of coordinates. Apart from that, they disconnect.